Healthcare encounters are a critical step in the delivery of quality healthcare to patients and in advancing patient care. Studies have shown that more than 70% of diagnoses and patient care directives come directly from these healthcare encounters. These visits typically involve examining the patients via auscultation, as well as listening to verbal symptom description from the patient. Studies have shown that only about 30 to 40% of chest auscultation diagnoses are accurate. Our project aims to create a system to record that doctor-patient interaction and quantify these chest sounds in order to improve the quality of diagnostic assessment. This will allow physicians to store and play back these sounds, visualize changes in chest sound frequency, and display key sound quality features to help improve the overall accuracy of diagnosis. The overall project goals were to, first and foremost, design and construct a system to capture sound components from patient encounters, identify and deconstruct these sounds into component elements, analyze, store, and display these sound components, and then integrate the sound component elements into an electronic health record. Following the completion of this project, the intent is to eventually transition to clinical trials.
Our team has identified the digital stethoscope's ability to record patient audio and transmit that audio as a critical design element 1. To ensure the clearest sound quality, we have decided to use ThinkLab's 1 digital stethoscope chest piece. This chest piece amplifies the capture sound approximately 100 times. This will ensure that the digital stethoscope will be able to capture sounds within the 100 Hz to 3000 Hz frequency range. Additionally, a rechargeable 1200 mAh lithium battery is included within the casing itself to power the Raspberry Pi Zero-W along with the chest piece. This choice of battery ensures that the digital stethoscope has enough power to last a minimum of 3 consecutive 30-minute doctor-patient encounters. Moreover, the digital stethoscope is sufficiently water resistant so that it can be sanitized and not have its functionalities affected. The digital stethoscope also has a start and end button to begin and end recording of each doctor-patient session, and the digital stethoscope casing dimension does not exceed 150 by 75 by 75 millimeters. Now moving on to the assembly process, the chest piece will be connected via 3.5 millimeter audio cable to connect to the Raspberry Pi controllers running Node.js. This will provide control over the device's power recording state and allows the audio to be saved and transmitted securely. Additionally, 2 LEDs to monitor the device's state will be enclosed within the casing itself, along with a single push button to allow various controls features such as power on and off, as well as start and end recording.
For our room sound collection setup, the team determined that the microphone should have at least a 24-bit depth and a 96 kHz resolution to ensure a good quality audio. After these specifications were met, the team elected to have 2 microphones arranged in the room. The first microphone is going to be able to capture the whole patient-physician interaction, and then the second microphone is going to focus specifically on the patient sounds. Both of these microphones are going to be connecting to a microcontroller that's going to be consisting of a Raspberry Pi 4 and an XLR interface. These sounds will then be sent over to the server via Wi-Fi for analysis.
The web app and server are the heart of the audio diagnostic system. With it, we can manage patients, connect to devices, and record, listen, and analyze audio. From the beginning, we established 2 primary requirements that the web app and server must meet. First, we declared that the sounds from the device must be sent to the server and saved privately for each patient. Second, we declared that the audio diagnostic system should have a user interface that enables the physician to view and play back audio files from the current appointment, along with audio files from the patient's previous appointments. We determined that the best design for the web app and server to meet these requirements involve using a MongoDB, Express, React, and Node.js stack. MongoDB was used to create the database responsible for saving user, patient, and device data. This allowed us to save user login information, basic patient data such as name, birthday, and sex, and device information that enables us to pair the device to the server. We used Node.js with the Express.js framework to create REST APIs and direct communication to and from the server. Node.js was the main controller that received the audio data from the device, sent them to the database, and displayed them to the user. React is a JavaScript library that we used for the user interface. This allowed us to speed up the development time and make a clean user interface.
Multiple studies have shown that spectral analysis of heart and lung sounds can help provide a more comprehensive assessment of lung sounds such as rhonchi and crackles, and heart sounds such as murmurs and gallops. These sounds are typically associated with specific frequencies as well as specific sound characteristics. Our team has elected to focus on extracting 3 sound components to help characterize these sounds from a signal processing perspective. The components selected are spectral flatness, spectral centroid, and zero crossing rate. The Python PyAudio analysis library was used to load in the audio files as well as to visualize the frequency spectrum for each signal. To perform the feature extraction portion, the Librosa library was used in Python because of its built-in feature extraction functions. The averages of each array of feature values were then taken to obtain the average of each feature over the whole signal to help characterize the spectrum of heart and lung audios. To verify these values, testing scripts were generated using MATLAB to compare the values of these features using sample audios to determine the accuracy of the Python analysis.
A product is nothing if it doesn't work properly. With this in mind, we set out to ensure that our product is secure and functions properly under various predictable and unpredictable conditions. To ensure security, we implemented cybersecurity practices to defend against common threats. This includes protecting user and patient data with strict user login credentials, encrypted password storage, and encrypted patient audio file storage. This also includes protection against attacks like cross-site scripting, session hijacking, and denial of service. To ensure functionality, we designed various layers of testing procedures. At the core of the system, we use unit testing to verify that every aspect of the system functions how it was designed to. This allowed us to test our code quickly under normal use cases along with side use cases. Along with unit testing, we developed a testing interface for each device. This testing method provided us the ability to test each device independently of the system to ensure their complete functionality. This allowed us to isolate and fix certain issues that may have otherwise been hard to detect through other means of testing. Our last means of testing was full system integration testing. This involved running through each foreseeable use case to verify proper functionality. This also included running through foreseeable issues that a user may make that would normally break the system. Even with all this testing and verification, there are bound to be unforeseeable use cases that could potentially break the system. In preparation of these, we included error handling that would alert or reroute the user instead of crashing the system.
Moving forward, the team would like to see the widespread use of the final product in basically any setting where medical sound diagnosis is necessary. In a clinical environment, the system would greatly assist physicians through saving data that's typically lost and giving them the ability to scan collected data for abnormal biomarkers. However, our team believes the most exciting ability of our system is its ability to be used by basically anyone, even outside of the clinical setting. Through our system, regular consumers with a desire to check on their hearts or breathing sounds are equipped with all the tools necessary for them to do so, while also being handed the means to analyze this data so they can interpret what their collected data means. This would also be a great leap forward in evolving healthcare to be able to provide consumers with the tools necessary to take charge of their own health in a tangible way. We hope our system's use will not only improve the efficiency and accuracy of the average healthcare encounter and subsequent diagnosis, but also empower normal people to be able to have more agency in understanding and participating in their own treatment and diagnosis.